Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 1. Limits and Continuity. Section 2.5. Continuity.
Lesson 4. Continuity of trig, exponential, and log functions. Part 2. Okay, so let's go ahead and do an example or two where we look at a couple of functions that involve all of these different types of functions that we have talked about. So here's an example that combines two types of functions that are discussed up here. I have the square root of x plus 5 divided by 1 minus e to the x. So I have a root function in the numerator, and notice that I have an exponential function in the denominator. Let's go ahead and think about where just the numerator, where the top is continuous. It's a square root, so it's an even root. And remember, that means that whatever is underneath the square root has to be something that is greater than or equal to 0. We can't take the square root of a negative, so x plus 5 cannot be less than 0. So that means that the top is going to be continuous when x is greater than or equal to negative 5. Let's think about the bottom. The bottom includes an exponential function. I guess you could go ahead and say that 1 is a constant function, so it's really a very simple polynomial function. And remember that polynomial functions are continuous everywhere. E to the x is an exponential function. We said exponential functions are continuous everywhere. In other words, for all real numbers x. So the difference between these two, if we thought of it as an f minus a g function, the difference between these two will also be continuous at every real number x. It will also be continuous everywhere. So the denominator is continuous everywhere. I'll just put down over here in parentheses 1 minus e to the x is continuous everywhere. And the top is continuous when x is greater than or equal to negative 5. So let's go ahead and think a little bit about this. I'm going to draw a number line here. And we know that the numerator of our expression is something that is continuous, 1, 2, 3, 4, 5, for all numbers x that are equal to negative 5 or greater. That's the numerator. The bottom is continuous everywhere, but remember that we said that f over g is continuous everywhere except where the denominator is 0. So if we find a value of x that makes this denominator 0, we would be in trouble. So let's think about that for a moment. The denominator is continuous everywhere, but the overall fraction won't be continuous at values of x that make the bottom 0. So we have to also ask the question, are there any values of x that would make the denominator, namely 1 minus e to the x, equal to 0? Well, that would mean 1 would be equal to e to the x. And can you think of a value of x for which e to that value is equal to 1? Well, remember that any base, any positive real number raised to the 0 is equal to 1. So if x were equal to 0, we would have a problem, because then e to the 0 would be equal to 1. And you can see then if I plug that in, 1 minus e to the 0 would be 1 minus 1. That would give me 0. So remember that we can't have the denominator equal to 0, and so we would not want x to be equal to 0. So I'm just going to put down here that x cannot be equal to 0. So even though the denominator of my expression is continuous everywhere, I'm not allowed to have a denominator overall that's equal to 0, and that occurs when x is equal to 0. So when we draw the picture of the points that would make this function continuous, we have to choose everything that's equal to or greater than -5, but we must also exclude the value x equals 0 because that makes my denominator 0. So I'd have to fix this up a little bit and put a hole in the arrow right here at x equals 0. And my function then, my overall function, if you think of it as an f over g, would be continuous for all x greater than or equal to -5 except for 0. Well, how would I write that as a final answer? In interval notation, I could say my given function is continuous on the intervals -5, the square bracket, up to 0. I want to exclude 0. And then all of those x values, or any x's that are from 0 going onwards forever, so up to positive infinity. And since I want any x's in here or here, you could put a union symbol in between those two. Okay, let's go ahead and do one more example of this type where we do some kind of combination, adding, subtracting, dividing of these different kinds of functions, special functions that we've already talked about. So we'll do one more example of that type. So on the next page, I'm asked really the same thing. I'm asked to determine where this function, h of t, is continuous. In this case, our input happens to be a t. You notice h of t is the inverse sine of t plus ln of t. But don't let that throw you, just using a different letter for the input value. And so here I really have the sum of two functions. So I have some function f plus some function g. And I'm asked to determine where f plus g is continuous, the values of t that make that continuous. And each of these functions, f and g individually, are of a type that we've talked about before. Inverse sine of t, of course, is an inverse trig function. And ln of t is a log function. Remember that ln of t just means the log base e of t. It's our shorthand notation for that. So that's just a particular base, and the base happens to be the natural log, so it happens to be the number e as a base. So let's go ahead and see if we can determine where each of these is continuous, and then we know that for any x value that makes both the inverse sine of t and ln of t continuous at the same time, that at that value of t, f plus g will also be continuous. So let's think about the inverse sine function first, and remember we said that the inverse sine function, all of the inverse trig functions, are continuous everywhere on their domains. So if I think about the inverse sine of t, it will be continuous everywhere on its domain. Well, what's the domain of the inverse sine function? We said the domain of the inverse sine function is all t values between -1 and 1. It's the same as the range of the sine of t function, the original sine function. So if I drew a little picture of that, what would that look like? Well, here's -1, here's 0, here's +1, and in another color I'll just draw the picture of the values. These are really values of t here. The values of t that would make the inverse sine function continuous. It's all t's between -1 and 1. Now we can consider ln of t. It is a log function, and we said all log functions are continuous everywhere on their domains, and the domain of any log function is going to be t values that are greater than 0. Remember that we can't put a negative value into an ln function, and we cannot put 0 into an ln function, but we can put in any positive number, any positive real number t into ln of t. So let's go ahead and just draw a picture for what its interval of continuity would look like. And ln of t will be continuous for any t values that are greater than or equal to 0. Well, that's great. We know that the inverse sine of t is continuous on this green interval, this closed green interval, and ln of t is continuous on this open interval. What we are really interested in, though, is where is the sum function inverse sine of t plus ln of t continuous. And just as we talked about earlier when we were talking about purely algebraic functions, we have to look for values of t that are both in this green set of numbers and in the red set of numbers at the same time. So we're looking for t values that would be in this green set and would be in the red set at the same time. So that's the kind of t value that we want. Those will be values where both inverse sine of t and ln of t are continuous, and therefore the sum is continuous. So since we want t's that are both in the green set and the red set at the same time, we really want the overlap of those two sets, or a more technical way of saying it is that we want the intersection of those two sets. So we can go ahead and say that the inverse sine of t plus ln of t is continuous on the intersection or the overlap of these two sets. And what is the overlap? Well, it looks like we can't have 0 because although 0 is in the green set, it is not in the red set since there's a hole in the graph here. So I can't have 0. I can't have any of these values between -1 and 0 because although they're in the green set, they are not also in the red set. But which numbers are in both sets? Well, it looks like values that are a little bit to the right of 0 and going all the way up to 1 are in both sets. So I can look at the values from 0 up to, and let's see, do I include 1? There's a solid dot here in the green set, and there's definitely a red dot here since this arrow goes to the right of 0 forever. So this point t equal 1 is in both sets. But I can't have anything beyond the value of 1 here because although those are values in the red set, they are not in the green set. So we're really looking at the overlap of the green and the red line. If you put those two on top of each other and see where they were both colored, you would end up getting this blue set down here. Well, let's just write that in interval notation so we could say it's continuous on, and this is a graph of where it's continuous, but in interval notation we would say it's all t values between 0 and 1, and I'd use an rounded parentheses at the 0 indicating I want a hole in my graph there, and a square bracket at 1 indicating I want to include the point t equal to 1 as well. Okay, let's go ahead and look at the next page, and we're going to look at one way of combining functions that we have not discussed yet, and talk about the continuity of what happens when we combine functions in that way. So our next topic here is continuity of the composition f circle g. Remember, f circle g is different than f dot g. When we write a dot there, we mean f times g. That's like what I've written here. F dot g means the product of those two functions. But f circle g means that we are composing the two functions. It means we're taking g of x and putting it inside the f of x function. So here's a little question. If f and g are continuous at a, we know f plus g is continuous at a, f minus g is continuous at a constant times f is continuous at a, f times g are continuous at a, and even f over g are continuous at a, provided g of a is not 0. I should add that in there. But what about f composed with g? And remember that f composed with g is the name of the composite function where we do f, not times, but of g of x. G of x becomes the input into f of x. So we plug x into g, we get some number out of it, and whatever number we get out of it goes into f. Okay, well, the answer to this question is a theorem that we are not going to try to prove. I believe it's proved in the appendix in the back of your textbook, but it is quite tricky to prove this, although not out of the realm of this course. But the theorem says that if G is continuous at a number A and F is continuous at the output of G at the number A, so if F is continuous at G of A, then the composite function f circle G of x, which again, remember, just means f of G of x, is continuous at A. So in a very sort of informal way, what we often say is that the composition of continuous functions is also continuous. So if you compose two continuous functions, you get a continuous function. And by continuous functions, we are really referring to functions that are continuous everywhere. That's kind of something we say is a little bit sloppy and is not as precise as this theorem, which talks about continuity at a particular number A. And so if you have a function, any function g that's continuous at a particular number A, as long as the outer function f is continuous at G of A, then the composite function will be continuous at that number A. Well, let's look at a couple of examples of this so that we can understand this theorem a little bit better. Of course, composition of functions is a little bit more complicated way of combining two functions than, say, multiplying two functions together. So that's why this theorem is a little bit more complicated to state. Well, suppose I have this function. H of x is equal to e, and all of this is in the exponent. It's e raised to the expression x squared minus 6x plus 5. And I'm trying to determine where this function is continuous, for which x values it is continuous. Well, we could think of this as a composition of two functions. And remember that we usually call g of x the inner function. So this is usually referred to as the inner function. And we call f of x the outer function. And in order to answer this question, first notice that this really is a composition of two functions. It's usually easiest to determine what the inner function is first. So we're going to figure out what g of x is first. It's the function that's inside of another function. And can you see what g of x is? We've done some problems in the past where we've pulled a function apart into two functions where one is inside the other. And if you look at our function e to the x squared minus 6x plus 5, notice that x squared minus 6x plus 5 is in the exponent, so it's in the position of x in the e to the x function. So it's inside of the e to the x function. So I would go ahead and say that g of x then is this inner function, one that I've drawn inside these parentheses. And if I declare g of x to be x squared minus 6x plus 5, what does that mean f of x has to be, so that when we compose f of g of x, we end up with e to the x squared minus 6x plus 5. F of x would have to be the function e to the x. And I hope you can see then that if I were to try to compose these two functions together, f of whatever I'm plugging in is e to whatever I'm plugging in, because f of anything is equal to e to that anything. So if I put g of x in as an input, it means I'll get e to the g of x over here. And of course, g of x is this polynomial x squared minus 6x plus 5. And so if I choose these for f and g and just check by actually composing those two, I do get the function h of x that was given. Okay, well that's great. Now we know about g of x and we know about f of x. So we know what those functions are. Now let's think about the continuity of each of those functions. Well, what type of function is g of x? We already mentioned that g of x is a polynomial. And where is a polynomial continuous? A polynomial is continuous everywhere. So I'm going to put that implies g of x is continuous everywhere at every real number x. Let's look at our outer function, e to the x. What kind of function is it? Well, it's an exponential function. So this is an exponential function. And what does that mean about its continuity? We already said that an exponential function is continuous everywhere. So this is also continuous everywhere. So let's go ahead now and think about where the composition is continuous. Well, g is continuous at a and f is continuous at g of a, then the composition is continuous at a. That's what our theorem said. But g, this polynomial, is continuous at any real number that I might choose a. So no matter what real number, I'll put any real number. No matter what real number a I choose, g will be continuous there. I plug a into g and I get some real number out. I'll say get out a real number. And f of x, which is e to the x, is also continuous at every real number. So no matter what real number I get out of g, f will be continuous there. So this composite function is going to be continuous at every real number that I might choose, because the inner function is continuous at every real number, and when we plug it into that inner function, we get some real number out, and the outer function will be continuous at that output. So this function, we could go ahead and say that h of x is a function that is continuous, or I should say h is continuous at every real number. Or you could say it is everywhere continuous. Or if you want to write down an interval, you could say it's continuous on the interval from minus infinity to infinity. That's where this little blue phrase comes from when we say that the composition of continuous functions is continuous. If you have an inner function that's continuous everywhere and an outer function, in this case e to the x, that's continuous everywhere, then the composition will be continuous at every real number x. Okay, let's go ahead and do one other example that has to do with composing functions. Here I have h of x is equal to ln of x plus 4. And notice this is not a product, but x plus 4 is a function that's going inside the natural log function. So if I ask you to determine the inner and the outer function, the function that's inside the ln function is what's inside these parentheses, namely x plus 4. So that is our inner function. And then for this to be equal to some f of g of x, if I declare the inner function to be x plus 4, what must the outer function be? Well, it would have to be the function ln of x. And just to check that, if you want to check quickly and find f of g of x, well, keep in mind that f of whatever I throw in, if I'm calling f of x ln of x, f of whatever I throw in is ln of whatever I throw in. So in particular, if I want f of g of x, it means I have to put g of x inside the ln function. And that means I would end up with ln of g of x, we said is x plus 4, so I get ln of x plus 4. So that checks, and we've determined what the inner and the outer function are correctly. Well, let's think about the continuity of the inner function first. G of x is equal to x plus 4. What kind of function is that? That's a polynomial. And where a polynomial is continuous, they're continuous on the whole real number line. They are continuous everywhere. So the inner function is continuous at every real number. But what about the outer function in this case, ln of x? Where is it continuous? Well, remember that unfortunately ln of x is not continuous everywhere. Ln of x is only continuous on its domain, and so it is continuous only for x greater than 0, we can't put 0 into a log function or a negative number into a log function. We just get something that's undefined. So the outer function is only continuous at inputs that are positive, that are greater than 0. And what is my input in this case? My input is actually the whole function g of x. What I have in this little sort of square wiggly box right here is my inner function g of x. And I want what's inside this ln function, this whole expression, to be something that is positive, something greater than 0. If this expression is equal to 0 or is something that is negative, then I am in trouble. So when I look at the overall function, the composite function h of x, which is ln of x plus 4, although the inner function is continuous everywhere, the outer function is only continuous when its inputs, namely x plus 4, are greater than 0. So we need x plus 4, whatever's inside this natural log expression, to be something that is positive, greater than 0. Well, for what values of x is that true? We just solve this inequality. I move the 4 over by adding negative 4 to both sides, and x would have to be strictly greater than negative 4. So h is continuous on the interval of x values x greater than negative 4. If you want to write it in interval notation, it would be from negative 4 to positive infinity. And that's what we would write as our final answer. So composite functions are a little more complicated. It's a more profound way of combining two functions, and so it's a little bit harder to analyze where a composite function is continuous, but I hope that these two examples helped. The next theorem that we talk about here is called a useful limit theorem. I'm going to skip that in this video because it is not as important as some of the other ideas in this section. So we're going to go ahead and turn ahead a couple of pages and look at the example that comes up 2 pages from here. Okay, before we leave this section on continuity, I want us to consider one other example that isn't of any of the types of functions that we've talked about. It's not a polynomial, it's none of the special functions we've talked about. It's not an exponential function or an inverse trig function. It's one of these piecewise functions, and it's a function that we considered in the last video. I think it was our last example in the last video, when we were talking about limits. So it was one of these crazy, weird sorts of functions. In this case, we said g of x is equal to, and we have 2 different rules for determining how to compute g of x, depending on not whether x is bigger or less than a number, as is sometimes done in piecewise functions, but depending on whether x is an irrational number or whether x is a rational number. So we define g of x to just be equal to the constant 0 if x is something that is rational. In other words, if x equals like 2/3 or 9/4, one integer over another is a rational number. But we use a completely different rule. G of x is equal to the input squared, x squared, if x is irrational. And examples of irrational numbers would be things like square root of 2, the 5th root of 5, anything that cannot be expressed in the form a over b, where a and b are both integers. So, for example, just to remind you of what this function would look like, if I found something like g of 3, and said, well, what's the output when the input is equal to 3? You have to ask yourself, is 3 a rational number? Well, it is. It could be written as 3 over 1 or 6 over 2. It can be written as one integer divided by another integer. So 3 is rational, and when I find g of a rational number, I have to use the bottom rule, and I always get 0 as an output value. So g of 3, because 3 is a rational number, would be equal to 0. If I asked you to find something like g of square root of 2, on the other hand, well, square root of 2 is an irrational number. It cannot be expressed as a fraction of integers, a quotient of integers. So since root 2 is irrational, I have to use the top rule to compute the output. And this says take whatever my input x is and square it. So my input is root 2. I would square that, and root 2 squared would be equal to 2. So g of root 2 would be equal to 2. So we have an entirely different rule for g of x depending on whether the input happens to be a rational number or whether it happens to be an irrational number. And you might remember we actually graphed this at the end of the last video, and g of x has a very interesting graph. Every time I put in a rational number, I get 0 as an output. So if I put in something like 3, we said, we get 0 as an output value. So I get a point right on the x-axis. And that's true for every rational number. Let me go ahead and put those in red. So we get a whole bunch of red dots down here along the x-axis. Every time I have a rational input, my dot, my point, is going to be right on the x-axis. On the other hand, for anything that's irrational, for example, root 2, which would be maybe right about here on the x-axis, I have to use the function y equals x squared to determine the output value. So I get an output value that's somewhere along that parabola y equal x squared. So it's like we have an infinite number of dots down here along the x-axis, and between those we have an infinite number of dots corresponding to irrational x's that are along this y equal x squared parabola. So we talked about that a little bit last time, and you might remember that last time we showed that the limit as x approaches 0 of this weird function g of x is equal to 0. And I think we had to use the squeeze theorem in order to, so I'll just remind you that we used the squeeze theorem in order to prove that this limit was equal to 0. You can kind of see it from the graph as we squeeze in on x equals 0. The outputs, although they keep jumping back and forth between the x-axis and this parabola, they do sort of settle down and get closer and closer to the number 0 as we approach 0 from either the right side or the left side. So that's what we did last time at the end of the last video discussing this particular function. We found that the limit as x approached 0 of g of x was equal to 0. We used the squeeze theorem. It took a bit of work to do that, to prove that that limit was equal to 0. Now we have a new question, and my new question is g continuous at x equals 0? Now you might look at this weird graph here and you might immediately think, well, I know the intuitive definition of continuity. The intuitive definition of continuity says that it will be continuous at 0 if I can draw the curve right through 0 without lifting my pen off the paper. And if I tried to draw this graph, I'd sort of be hopping up and down between the x-axis whenever I hit a rational input and this parabola, this dotted parabola here when I hit an irrational input. And it seems as if then I have to keep picking my pen off the paper even as I go through the value 0. Unfortunately, that intuitive definition of continuity, I think I warned you at the very beginning of this series of videos on continuity, that it can lead you astray. And that to determine whether this function is continuous at 0 or not, we have to apply the careful definition of continuity. The intuitive definition of continuity is the correct idea most of the time. But let's see what happens for this one weird example. We're wondering, is this continuous at x equals 0? Well, remember there are 3 conditions in the careful definition of continuity for whether or not g is continuous at a particular point, at x equals 0 in this case. The first thing is we have to ask ourselves, is g of 0 defined? That was our first condition. Well, let's try to answer that question. Is g of 0 defined? Well, in order to find g of 0, I have to decide if 0 is a rational or an irrational value. And since 0 can be written as a fraction that has an integer in the top and an integer in the bottom. For example, we could write it as 0 over 1. Actually, there are a lot of ways to do it. You could write it as 0 over 2, 0 over 100. It can be expressed as a over b, where a and b are both integers. So 0 is a rational number. And if the input is rational, we have to use the bottom rule to determine the output of g. Whenever my input is rational, and 0 is rational, the output is just always equal to the number 0. So the output of g when I plug 0 into the function is 0. Okay? So the first condition of the careful definition of continuity is satisfied. G of 0 is definitely defined and has an answer of 0. Okay, let's remember the second definition, second condition, I should say, in our definition, which is that the limit as x approaches 0 from both directions of g of x must exist. So we're wondering, does this limit exist? Well, it does exist. That's exactly what we proved at the end of the last video. We showed using the squeeze theorem that the limit as x approaches 0 of g of x is equal to 0. So it exists and equals to 0. So yes, it exists. And we found that the limit as x approaches 0 of g of x exists and is equal to the number 0. So our function g of x does satisfy the second definition, or the second condition, of the definition of continuity. Now let's check the third condition in our definition of continuity. The third condition was that the limit as x approaches 0 of g of x needs to be equal to the value of g at 0. So the value that g is getting closer and closer to as x approaches 0 must be the same as the value when we plug 0 into the function g. Well, is that true? We just got through saying in part 2 that the limit as x approaches 0 of g of x is equal to 0, something we proved in the last video. And we got through in part 1 saying that when we plug 0 into the function, since it is a rational number, we get 0 as an output. So the limit as x approaches 0 of g of x is 0, and g of 0 is 0. Those two are definitely equal to each other. So our function also satisfies the third condition of continuity at the point x equals 0. So this means we can say, therefore, I'll use my little shorthand notation for therefore, g is continuous at x equals 0. And it's really kind of a surprising result, because when you look at this function, it does not satisfy our intuitive idea of what this function would mean, what it would have to look like to be continuous at 0. I have to keep lifting my pen off the paper as I draw the graph through the point x equals 0, and yet it does satisfy our technical or precise definition of continuity at 0. So that's why we don't want to rely too much on an intuitive notion behind things. They can be helpful for us to understand a concept, but our mathematics will always rely on the careful or precise definitions, the mathematical definitions that we write down. So I wanted to show you that example as an example of a place where intuitive understanding of an idea can sometimes lead you astray. Well, I do have a final question down here. Is g continuous at any other x value? And again, it's hard to tell using our intuitive ideas, because we already said that that sort of fails us at x equals 0. So you might think about other values of x. For example, suppose we pick another value of x that's rational, such as x equal 3. You could go through the 3 conditions of continuity for x equal 3, and for that particular value, remember, first you would have to check that g of 3 is defined 3, it could be written as 3 over 1. It's a rational number, so the output would be 0. That's what we said right at the beginning when we were sort of getting used to what we meant by this definition for g of x. So since 3 is rational, the output is 0. And so yes, g of 3 is defined and ends up equaling 0. The second condition would say that the limit as x approaches 3 of g of x would have to exist. So we have to answer this question, does that limit exist? Well, if you thought about the graph, let me go ahead and kind of redraw the graph right here where it's a little bit larger. Here's x equal 3. I'm going to make this 9 on the y-axis and just crunch the y-scale a little bit. And our graph looks something like this. It has the dotted parabola, and these points all correspond to points whose x-coordinates are irrational, and then it has a whole bunch of dots right along the x-axis, and each of these points are points whose x-coordinates are rational. And what we're asking is, does the limit as we approach 3 from both the left and the right of this function exist? Well, for that limit to exist, it means the limit from the right has to exist, the limit from the left has to exist, and those two things have to be equal to each other. Let's try choosing a value of x that's a little bit to the right of 3. You could think of 3.1 or something like that. If that value happens to be a value of x that is rational, then we know the output is going to be 0. So if I pick something like 3.1, which is 3 1/10, which would be the same as 31/10, it's a rational number. Any terminating decimal will be a rational number. I would get an output value of 0 for that particular input value. But right next to 3.1 will be an irrational number. And if I choose that, a number that's a little bit closer to 3, and a little bit smaller than 3.1, if it's irrational, I would have to go up to the x-axis and hit the parabola and over, and I would end up at a value that's somewhere a little bit above 9. But there will always be another rational number even closer to 3, and so then I would end up with an output of 0 again on the y-axis, and closer still to the number 3 will be another irrational number, and so I'll go up to the parabola and over and pick something that's closer to 9. The question becomes, as we're getting closer and closer to 3, are the y's collecting around one single number on the y-axis? And unfortunately, they are not. They're collecting around two numbers, namely 0 and 9. And it's just because as we approach 3 from the right-hand side, there are an infinite number of rationals and irrationals getting ever closer to 3. And so we keep jumping back and forth between points whose y-coordinates are 0 and points whose y-coordinates are marching down towards 9. So the limit from the right-hand side does not exist. Remember, both the right-hand limit and the left-hand limit have to exist and be equal for the overall limit as x approaches 3 of g of x to exist. So unfortunately, no, this limit does not exist, and our function g fails the second condition of continuity in our careful definition of continuity at x equal 3. So g would not be continuous at x equal 3, a rational value. And if you want to, you can think yourself about what happens at an irrational number such as x equals root 2. Stop the video for a moment, think about that, and think about the first and at least the first and second condition in the definition of continuity, and see if you can convince yourself that this function also fails to be continuous at an irrational number such as x equals root 2. And then when you've given that a bit of thought, turn on the video again and we'll go through it together. Okay, well, let's think about this second one together. Let's see, if I were to just plug root 2 into my function, Well, that's what we plugged in up here at the beginning when we were trying to understand the function g of x. Root 2, we said, is an irrational number, so when we plug it in, we have to use the top rule to compute the output. And we said that when you plug root 2 in, you're going to do root 2 squared, that's my input x squared, and we get 2 as an output. So yes, it does satisfy condition 1, just like g satisfied condition 1 for x equal 3. The function is definitely defined at root 2. But now, if we try to think about the limit as x approaches root 2 of g of x, and we have to decide, does that limit exist, we run into problems that are similar to the problems that we talked about before. If I were to look at root 2, that's about 1.4, so it would come right about here on my x-axis. If I plug a number in, say that's a bit to the right of root 2 and happens to be a rational number, something like 1.5, say, I would get 0 as an output value. However, there is an irrational number that's just a little bit closer to root 2 and smaller than 1.5. So if I pick that number as an input, I would have to go up to the parabola and go over to the y-axis to get my output value, and that would give me an output value that's a little bit larger than the output value 2. If I get even closer to root 2, I can always find another rational number that is closer to root 2 still, and that would give me 0 as an output. But then there's another irrational number even closer to root 2 that would give me an output that is closing in on the number 2 on the y-axis. And so when I ask the question, as I approach square root of 2 from the right, do the y's collect around a single number on the y-axis? The answer is no, they don't. They collect around two different numbers, namely 0 and 2. And so the limit as I approach root 2 from the right of g of x does not exist. And therefore, the overall limit as I approach root 2 from both directions does not exist. And so, unfortunately, just like with x equals 3, that rational number, when x equals root 2, an irrational number, the limit does not exist, and it does not satisfy condition 2 of our careful definition of continuity. Well, if you think about it, we just chose one rational number and one irrational number to check, but the same argument would work for any number other than 0 itself. And so it turns out that g of x is a very interesting function. It's actually discontinuous everywhere at every real number x except for 0, where it is continuous. So what a bizarre function. It's discontinuous at every real number except for 1, except for x equals 0. So that's sort of an interesting conclusion. I'll say, so g is a function that is discontinuous at every real number except for 1. It's continuous at one number, x equals 0. And that's a very weird and bizarre function. So I'll let you think about that.